Yeah, let's continue the morning session. Our second speaker is Maurice Duits. Sorry, I still can't say it right. From KTH. My apologies. Who will tell us about the doubly periodic Aztec Diamond.
Okay, thank you very much. Let me start thanking Filippo for organizing this beautiful program and inviting me to be here. It's a great pleasure to be here. So indeed, I want to speak today about correlation functions for doubly periodic Aztec diamonds. I think we will see some more talks about this next week. Also, Kurt Johansson will talk about this this type of model. And I plan today to be quite basic. I really want to go through slowly through some recent progress we had on correlation functions of doubly periodically weighted Aztec diamonds. Okay, so and actually I will do everything for the Aztec diamond, but actually many of the techniques that will introduce today can be done more generally, also for hexagons, lozenge tilings or hexagons or different type of models. Okay, but I will just introduce two approaches for studying correlation functions of doubly periodic Aztec diamonds, and I will use that on the screen, and then I will work out a particular example and some recent results on a particular example called the biased 2x2 periodic Aztec diamond, and I will do that on the blackboard. So I hope I will manage with all the technology and the old and the new technology to make it work. Okay, so let me just start first with some pictures. Yesterday we already saw the Aztec diamond mentioned once, so I will also go over that. So some of the things I will speak about in the beginning are maybe well known to many of you in the audience, but I will be basic from the start to make sure that everybody is with me. So the picture on the left is something that we already saw yesterday. What I draw here is an Aztec diamond and a domino tiling of an Aztec diamond and a uniform sample of such a tiling. Okay, and we saw this already yesterday. And the nice thing about this picture is that you get an Arctic curve. All the randomness is inside the circle, and we have very interesting fluctuations here for these models. So this is a sort of a classical model that we have been analyzing. But actually what I want to go to is to a picture that is on the right, and I will introduce exactly how you can make that, how that is defined in a minute, but let's just have some fun and look at pictures. Here I take also an Aztec diamond, but now the weight on all the possible tilings is not uniform, but there is something called a two-periodic weighted tiling. Okay, so this is different weight and then just a uniform. You don't take something uniformly at random, but in a bit more complicated way. And what you see again is that there is a nice curve here. There is something, right, all the randomness inside, but you also see that there is two types of randomness. Okay, so there is some region here in the middle that looks a little bit different from the region here. Okay, so there is, of course, again, frozen corners, but then there is some sort of liquid region here where diamond-diamond correlations decay polynomial with the distance. But there is also another region here in the middle where the randomness is very different, and actually the diamond-diamond configurations there decay exponential with the distance, and this is often referred to as the gaseous region or the smooth disordered region. And for those of you that know more about this, if you would plot the height function here, the fluctuations of around the height function here, the height function here would have a flat profile in the middle, and the fluctuations would be of a very smaller order than the fluctuations here. Okay, so we would like to understand these type of pictures, and I don't want to go into too much detail on all the exciting things that you can sort of study in these pictures. I think Kurt will spend a lot of time talking about the region where these two different types of randomness meet. So I can recommend to go to that talk if you want to know more about this. Yes.
you say you have a flat profile, but if you consider the Domino timing of a rectangle, not Aztec, but you have a flat profile, but still I think it's true that you still have liquid, still a liquid phase.
No, I don't think so actually. There I don't think you have this boundary effect.
No, you don't have boundary, but you have a uniform phase, but is it gaseous or is it liquid?
Well, that depends on the correlation. So I don't know if I guess.
Just considering the uniform measurement that
then it should be liquid. Yes.
It's flat,
Yes. Okay. Yeah. Yes. Okay. Yes. Okay. So there is actually more nicer pictures here. You can continue. So the picture that I drew here on the right here is a 2x2 periodic Aztec diamond. This is sort of the simplest periodicity you can choose to actually create such a phase here. But if you increase sort of the periodicity, and I will be more specific in a minute about what I mean with that, you can construct all kinds of fascinating pictures. And we would like to study these pictures. Okay, so these are a little bit out of reach with techniques that we have so far developed, and that's sort of the goal of the project, to be able to handle such pictures. Okay, so you see that in this picture here, you see you have two different gaseous regions, and then you can ask, well, if I cook up some periodic model, I mean, how many of those regions can there be? And can I sort of quantify that? It all seems that there is some sort of curve around these regions also. Can I give, is this an algebraic curve? Can I give the formula for that? And all that kind of questions. Okay, so that's sort of the goal of the talk, is that I actually want to show some methods, or introduce some methods that could in principle be a start to start analyzing these kind of pictures. Okay, so let me get to the definition of this model. So let me start first with the Aztec Diamond, and let me start with the dimer configuration of the model. So this is sort of the Aztec Diamond graph, which is a bipartite graph, and a dimer configuration then is a perfect matching of this bipartite graph. Okay, so this is what we'll do. And then a two-periodic model is then a probability measure on all particular matchings of that bipartite graph, where that is constructed as follows. So the probability of having a particular matching is, of course, equal to the product of some weight function defined on the edges of the graph, and then you take all the edges that are in the matching, and then you take the product over all these weights. Okay. What we're going to assume is that these weights are assigned in a two-periodic, or in a periodic, doubly periodic way. So there are two different directions in the graph, and then these weights, they repeat themselves. So if I have the weight of this edge is maybe the weight of the same as this edge, and there is so on. Okay, so you can have here arbitrary. I mean, in the end, our Aztec diamond will be very large, so you can have arbitrary periodicity. But what I want to start with today, what I want to discuss in more detail today is a particular example. So here I drew a Aztec diamond again, and I will just put this on the board so that we can discuss this continuously. I will look at a 2x2 periodic tiling, or diamond model, where I have weights in the following way. I have two parameters, an A and an alpha. My alphas look a little bit on the A, so I hope it's going to be clear anyway. And there is another distribution here, A over alpha, and here I have a 1 over alpha. I want to be consistent with the papers we write, so I'll just keep on writing A and alpha. I hope it's clear what the difference is between the A and alpha in my handwriting. So A and alpha here are two numbers that are between 0 and 1, maybe including 1. And I assign these kind of configurations in a two-periodic way. So I have, maybe I can assign with a little color.
Sorry.
Yes?
You have, on the right, you have a times alpha and only 1 times A?
Yes, this is an A here. Thank you. Yeah. Right. Okay. So did I do this correctly? Yes. Here. So here I have right. So these ones, these are these ones. Right. So if I have a black vertex here, it's to the two. So it repeats it patterns like this. So this, if there's a blue circle around it, I give the weights like this. And if there is no blue circle around it, but it's a black vertex, then I give the weights like this. Okay? So let me say a little bit, what is this? So clearly, if the alpha equals the A equals 1, right? So that is the uniform case, right? So this is sort of a two-parameter deformation of the uniform case. There is also another case, if you would take, for example, alpha equals 1, then actually I don't see a difference between those pictures, right? If alpha equals 1, these are the same. And what you see is that the vertical dominoes, the vertical dimers have a weight A, and the horizontal have a weight 1. Okay? So that means that this is just sort of the biased Aztec diamond, where you just say that vertical dimers are punished, and you only want, so you favor the horizontal ones. Okay? So this is what we call a biased, right? So there is a bias here. And the bias is given by A. And this is, of course, if A is less than 1. Okay? So now you can also look at the A equals 1, so then there is no bias, but then you say that alpha is between 0 and 1, but not including 1. And this is the two-periodic Aztec diamond. Okay, so this is what we call, this is often referred to as the two-periodic Aztec diamond, and this has been studied by many authors also in the audience. And it was, for example, the picture I showed on the first slide. Okay? And you see, and the last case I want to discuss is that's sort of the interesting case. If both A and alpha are in 0, 1, but not equal to 1, then there is then this is what we call the biased two-periodic, biased 2 times 2 periodic Aztec diamond. Okay, and actually what I want to show you today also, hopefully I have time to do that, is that introducing this extra parameter, this extra bias, complicates the pictures in a quite nice way. Okay, yes?
I don't quite see, it seems to me that the two models you define are basically the same, but...
Sorry?
It seems to me that the two models that you define are the same if I change alpha into alpha minus 1.
Yes.
And then changing, isn't it the same? So it means that you allow alpha to be larger than 1?
Yeah, you could do that, yes.
Changing the white
yes.
Don't you get exactly the same?
Yes. There is, I mean, you will see also all the expressions will be symmetric in alpha and 1 over alpha, yeah.
But you have both of them in the same picture, right?
Yes.
Right.
Yes, both A and alpha, and these configurations.
Both left and right.
Yes. So the left ones are the black vertices, and the other are the other. Oh, sorry, that's the question. Sorry, now I understand. So yes, so I have two, right? So I assign the whites. Right. So these ones I put in here, right?
I could not see the blue.
I see. Okay, maybe I should have used a different color, right? And here I use this configuration. Okay, so just also quickly, maybe because also saw yesterday, I mean, to draw the pictures, you typically increase your diamonds and you draw little rectangles around it. So if you remove then the diamonds, you get this domino tiling of the Aztec diamond. And typically when we make pictures, we don't draw this kind of pictures, but we actually assign colors, and 4 colors. And the 4 colors, we have 4 colors because we have 2 different types of vertical dominoes, those that have a black square down and or a black square up. So the black square down, I give a yellow color, the black square up, I give a blue color. And then the similar for the horizontal, I turn them green and red. And then we get these type of pictures. So the right picture here, this is sort of the unbiased 2 times 2 periodic weight. So this is the case that when A equals 1. Okay? But I can also show here I do actually 2 different colors to make sure that it's sort of it's clear that we have some. Sometimes it's better to play with colors. I put some colors, 2 colors there, so that you can see this gaseous region a little bit better in this picture. And this is the bias to periodic Aztec diamond, and you see the difference also clearly here. Here it's sort of like there is a symmetry, right? You can just rotate by 90 degrees. Here it's sort of because of the bias for that the vertical dominoes are less likely. You see also that these corners become smaller. Okay. Sorry, that. No. These verticals. These are horizontal. Ah, yeah. I should have made the different color. Yes, you're right. That was the colors. The assigning of the color was maybe not perfect here. Why is this not working? Okay, I don't know why it's not working. Okay, great. Okay, so just so this 2 by 2 periodic Aztec diamond has been studied first by Sunil and Kurt, with some preparatory work by Sunil and Ben Young earlier, by computing the inverse Castellane matrix for this model. And if you give a nice closed formula or double integral formula for the inverse Castellane model, you can sort of do asymptotics by saddle point analysis. And this was done by Sunil and Kurt. And that formula they got in their analysis they also were able to analyze sort of this interface between this rough region and this smooth disordered region. Okay, but we will hear more about this on Tuesday. So what I want to talk about today is sort of 2 approaches to study these correlation functions, and not using the inverse Castellane matrix, but sort of the non-intersect picture. Okay, and we have sort of developed 2 different approaches. One is sort of an orthogonal polynomial approach, but slightly different from the usual orthogonal polynomial approach that you would expect for these models. And another approach is, so that's an approach I developed with Arno Kailas some years ago. And then later with a student, Thomas Berggren, we actually tried to mimic sort of the Schur process analog of the doubly periodic Schur process analog. And then we found that finding the problem of finding correlation functions is related to Wiener-Hopf factorizations. And I want to explain mostly today on this method, but I will also say a few words about matrix-valued orthogonal polynomials. Okay, so first of all, I have to go to non-intersecting paths. I will do this quickly because I think this is quite well known in this audience. We have the DR paths, and the DR paths you can construct by drawing sort of line segments on each of these dominoes. You go either upright or down right if it's sort of a domino that is vertical, but depending on whether the black square is in the bottom or on the top, or you go straight if it's a horizontal domino with a black square on the left, and you do nothing if the black square is on the right. And if you the R, is it so maybe louder, maybe later. We don't have a mask. Okay, so these paths here, we get some paths that are never intersecting, and they go from the left to the right. Okay, and these paths completely determine your tiling. So you could just as well study these paths instead of your tiling. Okay, so now what I want to do is actually, I mean, one of the problems with these paths, what I don't like, is that this path always is much shorter than the top. Okay, and then you want to make these longer so that, you know, things should be more equal. And we saw yesterday a way of doing it. I think everybody has his way of doing it. So I want to give two ways of doing it, which also correspond to the two different approaches that I give. Okay, so the way I want to do it, I like to do it is actually to draw a slightly smaller, just one size smaller Aztec diamond, just here. And then I'm going to tile a larger region that just consists of the union of the two. Okay? And if you do that and you draw these paths, then you get paths that go nicely from left to right, and they're sort of more equal in length. Now, okay, I'm doing a different region, so that might be problematic, but you can actually verify combinatorially that it's not possible to have a domino that is on both Aztec diamonds. So it always decouples. So you can just as well look at this one. Okay, so this one is for one approach that I like. Another approach that is maybe more closer to also the approach that Kurt used is actually to insert a sort of a piece in between those two Aztec diamonds, sort of a corridor of an arbitrary length, okay, of a particular shape. You know, this is a very particular shape. But because of this particular shape, the way you tile this corridor is just, there's only one way of doing it. Otherwise, you get a contradiction. So okay, then I have a very strangely shaped a domain, but it basically completely decouples. And the nice thing about this is I can make this corridor as long as I want, and in the end we will send it to infinity. Okay? Yes, so here the size is, this one is one less than the other. Yeah. Okay, so but anyway, the nice thing, I will get back to that. Oh, why is that? Why can I not go back? Yes, okay. So I will come back to this picture later. But the message here is that, you know, studying these tilings of these Aztec diamonds is the same thing as studying non-intersecting paths, and that's what I will do now. Okay, so now I will just forget about the tiling picture. I will immediately go to these to non-intersecting paths on graphs. Okay, so this is just. And okay, so if you didn't follow the domino tiling so far, I think everybody did, but then you can just start again. Okay. So this graph here is a graph that is typically associated to the Aztec diamond, where you have a graph where you have two n columns, where capital N is sort of the size of the Aztec diamond you want to study. But here it's just two n columns that we get, and so it's part of the lattice graph. And then we draw edges depending on if you are in an odd or an even column. In the odd columns, we just go straight or we go one up. And in the even columns, we just go straight and then we go down. Okay? And I glue all those together. Okay, so I look at this graph. And what I'm going to do at this graph is I'm also going to assign weights on this graph, and I also do this in a two-periodic way. Here I have P and Qs because they are different from the R and the S that I had in the first slide. They don't have to be the same. Okay? And this is my graph, and I'm going to assign weights on that. Okay? And I will also say that the weights you assign, I will do that in such a way that it's sort of consistent with this particular case. And let me just say that for the non-intersecting path picture, so for this graph, to make the connection to this model, what you need to do is the following. So you get a 1 here, an A here, an A here, and then here I'll put an A over alpha, and an alpha inverse on this one, then an A times alpha here, and then an alpha here. Okay, so again, these weights, they have the A, there is a weight A for the slanted parts, and then there is the alpha, an alpha inverse. So alpha inverse is in this part, and then alpha is here. And then I just start copying this, you know, repeat this pattern so that I fill this entire region. Okay? And this sort of matches this example here. This is what you should think about. Okay, if you do that, the next step is to look at non-intersecting paths. So these are sort of these extended DR paths. That's sort of what you should think about. We're going to put them starting points at 0, 0 to Pn minus 1, where P is this sort of periodicity. Okay, we had periodicity P and Q, they will come all the time. So this is 2 in this direction, but it's actually only 1 in this direction, because it will just this part will just repeat. I put a 2 here. That's not so relevant, but we'll just have this piece is repeated. Okay. So we will start at these parts, and then we will end at these parts. Okay? And then, of course, we take all the paths that are non-intersecting, go from left to right, and then the probability of having a particular configuration is just the product of all the weights in the path of the edges. Okay, that's just in the usual way. Okay, so we want to find sort of the correlation functions for such a thing, and of course we have the My integer p is in this case it's 2, but it's sort of the periodicity in the vertical direction. So I just make sure that I have like p and paths so that it sort of matches the periodicity. You don't really need to have p here, but it's for simplicity. The formulas get nicer if you do it.
You mean that
Yes. You can do p in this direction, q in that direction. In this example, p is 2 and q equals 1. Okay, so then I will take a point process in the usual way. If you have a configuration of paths, a random configuration of paths, then I will make a point process, what you're saying at each sort of like, at each section here where the path is, right? So I'll put points on these paths, and if there's an ambiguity, if there are several sort of points that I could put, I put it on the lowest one, right? That's just that's my. So here I have a configuration of of points, and on each vertical section I have exactly Pn of those. Okay. Now what I'm going to do, and this is the first important step, is that I'm going to introduce transition matrices, and this will actually help me. These will be very important. So the transition matrices, they are defined. They go basically like from one section to the next one, Tm. And they're just the product of all the weights that you get from going from this point to that point, right? So there is a unique path, right? For each 2 points, there is a unique path that connects these points, and then I just take the product of those weights here. Okay. Okay. So x for here. So in this case, we have the x is the horizontal coordinate. Sorry, the vertical coordinate. Okay. No, not really. So what I drew here, I should have done that here. This point is mx, and this point is m plus 1 y. Yeah, I should have drawn that. Okay. So these are transition matrices, and sort of the correlation functions, they can be expressed in terms of these transition matrices. Now, important consequence of the fact that I have a vertical periodicity is that these transition matrices also have this periodicity. If I add p and both, I just translate all this part by p. Since the weights were p periodic, this transition matrix doesn't change, right? So so adding p in both coordinates doesn't change the value of the matrix. Okay. And then also if there is a periodicity in the horizontal periodicity, and that just means that at some point these transition matrices, they repeat themselves, right? Okay. But important, the horizontal periodicity we can forget for now. Let's go to the vertical periodicity. The vertical periodicity means basically that my transition probabilities, my transition matrices are block Toeplitz matrices. Because they basically only depend here, so at a point px plus r and piy plus s, they actually only depend on the value of x and y here for each, right? So they have this block structure, let me put it like this. They have a block structure. Because if I know what this block here, then I know everything on this block too, because this is just a translation by p plus p, right? So it's sort of constant along these diagonals, right? So these transition matrices are block Toeplitz, doubly infinite block Toeplitz matrices. So these block Toeplitz matrices, they typically have what we call a symbol, which is just it's just a matrix valued function in this case, where these coefficients are the the blocks that you find on diagonal. So it's a Fourier transform of these blocks.
The sum in X is infinite.
The sum in X is infinite for this case, yes. Yes, it's overall, it's doubly infinite, this matrix. It's important, doubly infinite. Okay, and this is just basically the Fourier transform. I mean, these are just the Fourier coefficients of the phi m, right? And it's all matrix valued in this case, but scalar valued would be just be a Fourier, right? And the nice thing about these transition matrices is that if you take a product of them, then it's just the same. Then it's just a Toeplitz matrix where you take the product of the symbols, and that's an important property that we need. Okay.
There's something I don't understand. You define the transition matrix in last slide as product of something over edges, but there is only one edge in this dimension, and also
no, so if I go from X to My, I have several edges here, maybe, right?
Because it's for any, it's not for adjacent.
No, it's not adjacent. Right? Yes. But actually, if you go from here to there, then I can go only straight, or I can go up, and that's it.
Right.
So that matrix is very simple. It has only two diagonals that are non-trivial. But from this one to this one, it's actually not so trivial, right? So actually, let me write up. Maybe I can just tell you immediately what is here the transition matrices. So the phi m in this case, it's either you are at an odd one or at an even step. So at the odd one here, phi odd, this matrix looks as follows. It's an alpha times A times alpha Z of A times alpha inverse, and this is if m is odd. And phi E, this is going to be 1 over 1 minus A squared over Z of 1A over Z 1. Even. Okay? So here there is no alpha, here there is a, right? And the fact that we have this factor, the scalar factor 1 over 1 minus A squared over Z, this sort of shows that you can go down arbitrarily, because if you do a geometric series, right, so that this you can think of this as sort of a geometric jump, but it's not really geometric, it has this block structure. And this is a Bernoulli jump, but you have this Bernoulli, you have a block structure also there. Okay? Okay? Yeah? Okay, very good. So then just some standard things is that the LGV theorem here tells you just that the probability of having points at some certain configurations here is just the product of determinants. And from there, the Einstein theorem tells you that things are determinantal, saying that the probability of having paths going to these blue points is equal to the determinant of some kernel. Okay, this is sort of general determinantal point process theory. And what we want to know is what happens with this kernel. Okay. We want to understand what is the formulation, what we want to see the structure of this correlation kernel. And the Einstein theorem actually even gives you a formula in terms of what we call the Gram matrix, which in this case is the following. So you have a matrix, and it should be, it's a block matrix. So and the jkth block is equal to this product of these transition matrices at kj and 3, kj block of the product of those, and just by the fact that you have this, that the product of these transition matrices, just the product of the symbols, gives you the Fourier coefficients of this function here. Okay, and these are just these matrix valued symbols that I have here. Okay. And then the thing is, you have to invert this matrix, and once you invert this matrix, you can study the correlations. So you get the formula for the correlation kernel involves the inverse of this matrix, right? So you need to invert this matrix, but the problem with this matrix is it's large, because n will be large, right? So then there are two different ways you typically do this. The standard ways of either you try to change your basis. This is the orthogonal polynomial method. You actually start changing your matrix G by doing column and operations and row operations to make sure that this matrix becomes diagonal. Okay, this is the orthogonal polynomial method in random matrix theory. Another method is just by really trying to compute the inverse, find a nice formula for the inverse, and the only way you can, but actually that is going to be complicated. But it turns out that you can actually do that by a Wiener-Hopf factorization when the size of the matrix goes to infinity. So for finite size, you cannot invert this or not easily invert this, but when things go to infinity, when you look at the infinite matrix, then you can actually do it. Yes?
What I didn't know is that the Hermet-Tarp theorem or the method of orthogonal, you know they work when phi is a matrix. So you say that everything works against phi.
Sorry, what that?
So here, your phi is a matrix.
Yes.
Matrix. So I knew it about when phi is a scalar, but you say everything works.
Well, that's yeah. So that's the work. Yes. So this is, if phi is a scalar and you set n to infinity, then this would be the Schur process, and then you can invert, and then you can find this inverse of this matrix by that's sort of the Schur process. So this is the Schur process analog, and this is some different analog. So I want to maybe say a few words about each method. Okay. So the first method is now that we get this matrix valued orthogonal polynomial. So how does that work? Yeah.
This Wiener-Hopf factorization,
Yes.
is it when you're lucky and you know Wiener-Hopf factorization, or is there a regular way to get it in general case?
Yeah, so how much time do I have, actually? 20 minutes. You know what, I'm going to skip the matrix valued orthogonal polynomials and speak by the Wiener-Hopf factorization method only. Then I can actually do this example also. So I will just maybe briefly say something about these matrix valued orthogonal polynomials, and I will answer this question in more detail by the talk. Is that you can actually, like, you can change your basis and by column operation, row operations on the matrix G, instead of sort of this Z to the J minus K, you can change it into polynomials, general matrix valued polynomials Pj and Qk, and then you can organize it in such a way that it's orthogonal, okay? And then you can show that such polynomials exist, and these are sort of bi-orthogonal matrix valued orthogonal polynomials, and these you can use to build the kernel by first looking at this reproducing kernel, but then it's not then the correlation kernel is not the reproducing kernel. No, it's actually much more complicated. It's a double integral formula where you get this reproducing kernel, but you also get these extra factors here, so you get a double integral formula of this. Okay, so this method actually would be, so I don't know how many people like Riemann-Hilbert, but if you want to do asymptotics now of these models, what you can do is first you do these asymptotics for the orthogonal polynomials, which are now matrix valued orthogonal polynomials. Then you compute that asymptotics, you insert it in this double integral formula, and as a bonus you need to do a steepest descent analysis on the double integral formula. So this is computationally quite involved, okay? So, but actually, the nice thing about this is this works also in the hexagon. Like if you would look at a finite hexagon, Lossensteinings of finite hexagons, and then I don't know any other method to do it, because then you're really as far away from the Schur class as possible. And then this is the way you should do it, and you should just sit through it and develop a theory. And then the first depressing fact is that there is not really a standard way of doing Riemann-Hilbert analysis for matrix valued orthogonal polynomials. Okay, so you need to develop that, and we are currently also developing that kind of tools.
Because you don't have Christoffel-Darboux formula.
There is a Christoffel-Darboux formula, but this, I mean, just for general matrix valued orthogonal polynomials, the asymptotics is. The problem is that matrix valued orthogonal polynomials are much more complicated than scalar, and you need to sort of restrict yourself to subclasses to actually do asymptotics. And this is one subclass, the ones that come from these tiling models, and then you can maybe sit there and try to understand things, and we're developing machinery to do that. Yes. Okay, so the good thing is that when you look at the Aztec Diamond, you don't need to do these matrix valued orthogonal polynomials. Or actually, if you would do it, and this is what we did originally with Arno, is that we actually found that these matrix valued orthogonal polynomials for the Aztec Diamond are very explicit. They're very simple. And this was a bit of a surprise to us. So we could derive quite a nice, simple correlation, double integral formula for the correlation functions, because these polynomials were so simple. The question is, why are they so simple? So, well, similar like the Kravchuk polynomials, they're also easier than the Hahn polynomials. I mean, it's because there is some kind of sure process structure in the background. So that's sort of the second part that I want to talk about. So now in the second approach, I just want to use the fact that I look at this part here, that I can send n to infinity, the small n to infinity. So the capital N, this is the size of these Aztec diamonds, but I send the small n, that's the number of paths, it's the length of this corridor, to infinity. Okay? And that limit is easier. We can actually analyze it. And what happens then is that you can actually compute the asymptotics of these matrix valued orthogonal polynomials in a trivial way. And they involve the Wiener-Hopf factorization. Okay, so there we come with the Wiener-Hopf factorization. So what I take here is the phi. This is the product of these transition matrices. If you can find a Wiener-Hopf factorization phi plus times phi minus and a phi minus phi plus tilde, and they are not the same because it's not scalar, right? Such that the phi plus is, and its inverse, and phi, and also for the tilde, they are analytic inside the circle, and the phi minus is analytic outside the circle, and at infinity, these phi minus, they are normalized so that they go to 1. If you can find this factorization, then you can actually find a nice expression for the double integral expression for the correlation kernel. Okay? And now I speak here about limit at the bottom. Why do I do that? Because remember, we have two Aztec diamonds, right? When we go to n to infinity, we have to choose which one are we going to look at. Now we also have two factorizations. And one is for the bottom and the other one is for the top. Okay? So what happens is that if you look at the bottom, sort of the smaller Aztec diamond, then you need the phi minus and the phi plus without the tilde. And if you look at the top, then you need the tildes. So this is at the top. And they're also swapped, yes. And okay, so this formula, those of you who don't know sure processes, they will recognize this formula. The scalar case, this is exactly the formula for the sure process. Yeah?
In your Wiener-Hopf factorization,
yeah.
On the slide, it seems to depend on large n.
Yes.
So
yes.
So you have to do how does it depend on n?
Exactly. So that's the next problem, is that we need to find this factorization, and it depends on capital, and we have many of those terms. So now, in the scalar case, so if the phis are actually scalar, then finding a Wiener-Hopf factorization is rather trivial, because you get a bunch of terms. Each one of them is good either inside the circle or outside the circle, and you just reorganize terms. And life is easy. You just get your factorization for free, and tildes don't matter. Yeah. So here you have, So these are scalar. So here, I mean the phis here, they are either of the form. In this case, they are either of the form 1 plus like this is a Bernoulli jump, because this is Bernoulli jump up or Bernoulli jump down, or it's like a geometric jump up or down. Okay, so these are sort of the building blocks for the sure process. Yes. Yeah. Okay, but then there it's rather easy. You just reorganize terms. The problem is, of course, if you are matrix valued, you cannot really reorganize terms, because this is just simply does not work. So what do you do then? Well, there is a next best thing that you can do is that you actually can, that all these matrices, they depend on parameters. If I would want to change these matrices, I can actually change the order, but then I have to update the parameters. The parameters change. And these parameters change in a very non-trivial way. But you can still write down some formulas for that. And this is sort of like a birational map, and I learned this from the paper in Lampiliavsky, but I think it was known before. There is some nice sort of like structures behind this that tell you how to change two matrices, or at least one way, because it's actually not unique to do this. You can always put a diagonal matrix in between, and then the inverse, multiply phi k by some matrix, constant matrix, right, from the right, and then with the inverse from the left. But that doesn't, so it's not really unique, but this tells you a way of doing things, okay? And this map has an, yeah, okay, but let me not talk too much about that. It's, in principle, it's possible, so you can reorganize things, but now we come to the question, capital N is still there, and capital N is going to be large. Are we going to do this infinitely many times? This is going to be problematic. So if you do this, this is a mess. The map is there, but it's a mess. But now we are going to use the horizontal periodicity in the horizontal direction. Right? I haven't used that. So these matrices, these transition matrices, they repeat each other, right? I mean, in my example here, it was already after 2 times, right? So there is I can write the phi, this full product, as an AZ to the n, where A is sort of like phi 1 to phi 2k, and then after these are just the different ones, and then it repeats itself. Okay? Yes, is this okay? So now comes the thing. What you can do is that, suppose, like, okay, so what we are looking at is a phi that is sort of a power, a large power of an A. I also replaced n by 2k qn, so to make things a little bit more readable along the way. Okay, we get large powers of this A. Now, suppose you can do a factorization of the A plus, of A, and A plus and A minus. What you do then is you write this A as an A plus, A minus, then you write out this factor. I can put actually an A plus in front and A minus in the end, and then I get an A minus A plus to the power n minus 1. Right? So, but then you can say, okay, then I did one step, here I stop, because now I get a new matrix, A tilde, which is just the factorization, but then I swap the 2 matrices, and then I start factorizing that. Right? And then I continue, and I continue, and I continue. So then I start with a matrix A, I get a matrix A tilde, find a factorization, swap the matrices, I get an A double tilde, and so on, and so on. If I do that, right, so I just do this iteratively, at each time I just compute a factorization, at each step j, I do a factorization like this, I swap the matrices, I get a new matrix, and I do the same thing again, I get actually my factorization in this form, okay? But now again, this is a problem because, we need to do this n times, capital N times. So the whole question is, can we find this flow of matrices? Can we control this flow of matrices? Okay? So now it turns out, and I will do this now, just be very brief about this, that actually in these cases that if I set A equals 1 here, in this example, if I set A equals 1, turns out if you do this 4 times, you're back to the original matrix. Your flow is periodic. And if its flow is periodic, okay, then it's the period.
You do what?
So you do this 4 times, like you compute, like you start with an A, you do the factorization, A plus, A minus, and then you swap the 2 matrices. So right here, A is this, I swap the order, and then I have a new matrix. And I do this now with the A tilde, and I do it then again, and again, and again. After 4 times, I'm back to A.
There is no flow, just what map that is power 4 is...
Right, but you iterate the map, right? Yeah. You iterate the map.
Yes.
Yeah, yeah, yeah. Yes, yeah, yeah, yes. So okay. So if you can do that, then actually you can trace things. You can actually write down double integral formula. Then these factorizations become rather tangible, and you can actually do asymptotics with them. Okay, I don't show you why, but in these cases where we worked out these cases, we could just trace this somehow. okay? But for if A is less than 1, it doesn't, in this model, for example, you are not necessarily as lucky, and it will not sort of, you know, it becomes very complicated. But now comes the nice thing, and this is something that we did recently, is that in this particular case, when A is going to be less, you can still actually study this sort of this chain of matrices, because you can linearize it. And this is because of some very nice structures that were done already in the 70s or 80s, I believe. There is Veselov and I forgot the second author now. They introduced somehow that you can actually linearize this flow. And I want to show maybe, I don't know how much time do I have, but I would like to show how you can linearize that flow, just maybe just the final sort of to answer this question. Okay, so one of the starting points of if you want to linearize this flow is the following. So what we do is this, right? Is this map that you factorize A in this way and then you swap it, right? Now there is obviously an invariant for this swapping, is that the trace and the determinant don't change, right? So the spectral curve of A tilde is the same as the spectral curve of A. So there is so the spectral curve doesn't change, right? So what you can actually show is that this is sort of a, you know, you get some dynamical system on matrices that have the same spectral curve. Okay. It's just AZ minus lambda equals a determinant of that is 0. Okay. So let me just write this quickly for this particular case, because it becomes quite interesting. Let me start with this matrices. So what I need to do here is to compute this A, right, first. So the A is basically just the phi 0 times the phi E, okay? And let's just forget about the scalar factor. So it's just this matrix times that matrix, okay? Right? So okay, so this is going to be alpha A inverse, A alpha Z, A inverse, and get 1 A over Z, and then this. And let's forget about the scalar term, right? Because that's something you can always put wherever you want it. So that's a harmless thing. Okay, so if you would write out this product, then you will see that this matrix is actually of the form. Well, let's say that it's of this form. And the Aij are positive, and the Bij also positive. Huh? Okay, so it's a matrix of this form, right? And so it's constant, and there is a Z dependence. It's a polynomial on Z in this entry, and it's a 1 over Z in this entry. Okay. Now what I will do here is now look at this, a subset of this indexed by A and alpha, which is just consists of all these matrices. Let's call them A. That are in this set, but they have the determinant of A is exactly this determinant of this matrix here. Okay, so this is you can just compute it. It's 1 minus A squared over Z times 1 minus A squared times Z. Okay, and then also I take the trace of A is going to be is actually simple. It's alpha plus 1 over alpha, and times A squared plus 1, okay? Okay, because these, when I start changing these matrices, I stay in this set, because the determinant and trace don't change, right? That's just if I order the order in the product. Now, for technical reasons, I will also assume that this actually, the B12 entry here is going to be equal to A times alpha, okay? And the reason I do that is that it's something that I didn't really say, but this factorization is not really unique. And by taking that extra assumption, we actually have a uniqueness of the factorization. Okay? So now there is just a little lemma. So if you have an A in my set, then there exists unique A plus and A minus such that the A plus is the A plus and its inverse are analytic inside so analytic for Z less than 1 to A minus is analytic outside. And now comes the thing, and this is why I needed the third condition. If I change these matrices, if I change the order of the matrices, then this is also in my set. Okay, this is not entirely trivial because of the third condition, but actually it's true, and this actually determines this factorization uniquely.
You probably also want A equals A plus A minus?
So, oh yeah, yes, of course, yes. I should write this. This is A plus A minus. Yes, exactly, yes. Sorry, what that?
Your A plus and A minus are not necessarily in your S.
No, not necessarily. No, actually they will not, because the coefficient is always strictly positive. And they will actually not be there. No. But that means that I can sort of define this map now, like I can just define a map S that just acts on this space to itself. And it's, right, it sends A plus, A minus to, like this product, to just its conjugate. Okay, so this is really, and this is the map we want to understand, right? Okay, so now, I'll go, sorry if I go slightly over time, but there is a very nice punchline, so I hope people don't mind. Otherwise, oh, no, I don't want to do this. So now there is a nice way. We can parameterize this space by an elliptic curve. Okay, very explicit elliptic curve. So the elliptic curve here is the following. It's just all points in R such that the y squared equals x squared plus 4 times x minus a squared times x minus a minus, and then here divided by a plus 1 over a times alpha plus 1 over alpha squared. I trust you believe what I write here, but the point is that this is a third degree in x, so this is an elliptic curve. Okay, and if you can draw it, it has, in this case, because of the parameters, it has two parts. Okay. AD.
AB, right? Because matrix in SA1. So E is bijective with SA1, right?
Yes, it will. No, not A, not E itself. No, it will come. Yes, yeah. So it has two components here. Okay, and this component is E minus, and here this is what we call E plus, but I don't care. So it's actually E minus that is a projection that is in a one-to-one correspondence with SA, and it's because this elliptic curve is just a sort of a different reparameterization of the spectral curve, actually, which is the same. So this is sort of this is basically the spectral curve. Okay, now elliptic curves have a nice group structure, right? So you can add points with each other. So let me take a particular point here. 1 over a squared, 1 over a squared. Okay? Because if x is 1 over a squared, then this is 0, and then y equals x. So that's a point on the curve, right? Okay, so you can actually add a point on this curve to a point, say, on E minus. Okay? And how do you do that? Now let me draw it a little bit bigger. Suppose I have an E minus here. So here is a point here. Let me take a point here. So if you draw this, you need the group action is described geometrically by drawing a line between this point and this point. This gives me a unique intersection point, which is also an E minus, and then it's this point. And then you need to reflect it with the y-axis, so you get a point here. Okay, so So this is my point xj to, well, that's point x, y, then this is the point xy plus 1 over a squared, 1 over a squared. Yeah? So this is the group action on the elliptic curve. You can add this classical standard, although I didn't know it before the, the project, but I will admit. Anyway, okay, so now I can look at a flow on this curve that is just sigma, which is acting on E minus only. And it's also clear, right, because if I add this point to a point on E minus, it becomes a point on E minus again, because wherever you cut this, if you take the, if you draw a line, it will always cut in another point at E minus, right? So this curve, this here, is just adding xy, just mapping it just at this point. And now my point is that actually, and then I will stop, is that these flows are the same. Okay, so that there is a theorem now that says that there exists a bijection pi that goes from E minus to SA alpha, such that the pi of, if I first apply sigma and then pi, then it's the same as doing that flow after I applied pi. And this is very nice. This means that you actually trace your flow in a more concrete way, right? Because it's elliptic curve, you can use this elliptic curve. And it also allows you to understand, because we would really like situations where the flow is periodic. You can also understand, you can try to find points where this flow is periodic, because the torsion points for the elliptic curve are well understood. Torsion group of the elliptic curve is well understood. And actually what we will see then is actually you can compute this, that if A equals 1, then it's a torsion point of order 4. But there are also other relations between A and alpha that give you that this point is a torsion point of order 6. And this is something we work out also in our paper. And then actually what we do also in the paper is that we actually use the fact that if you have a torsion point, you can actually do asymptotic analysis, and you can really prove, for example, these different gaseous regions in the Aztec Diamond. I apologize for going over time. Thank you.
Questions? More questions?
You mentioned B-rational, I think you work of Lam and Pilasky, and with
right.
this way to exchange two matrices by changing parameters. So this is reminiscent of Young-Baxter. Is there a general connection?
Yeah. Well, let me not get into things that I don't really understand super well. But one thing I can say is that actually, and this is something that we are some project I'm doing now together with Sunil, and it's not finished yet, but I think one of the nice things about this map there is that it seems that this way of doing a Wiener-Hopf factorization and using these rules of this birational map actually is sort of also related to the shuffling algorithm. So this Wiener-Hopf can be sort of thought about as some representation of shuffling. Yes. But okay, we have to finish the details, so I'm a little bit, yeah, this is ongoing work, yeah.
I have a more analytic question. Diffusive limit of the two periodic Aztec Diamond, some sort of non-intersecting Brownian motions with some sort of two periodicity, Dyson Brownian motions or something. Have people considered that?
I'm not sure what you mean, but it's very important to have like a discrete structure here, right? So I don't know what would you make? I mean, Dyson. What would you do exactly?
Well, take continuous space and time, I guess.
Right.
But still some finite number of paths. Does it make sense?
Yeah. You want one. I don't know. I don't know if this has. I don't know if there is. I mean, I'm not sure if it's a.
Or you can do it. Maybe in the ordinary Aztec Diamond with the curve, they are dependent on that.
That's okay. I see. That's what you're. Okay.
There are other models where you get
Yeah, in the ordinary Aztec Diamond,
I see. Okay. That's okay. That's what you are. Okay.
Okay, I think it's time to conclude, so let's thank the speaker again.